All right, hello and welcome to the next episode of 3D and 30, Accelerating AM with AI-driven design. 3D and 30 is Velo3D's LinkedIn Live and YouTube Live platform. We host these about every 2 to 3 weeks, depending on the schedules. So make sure you follow us on LinkedIn to see what the latest schedule is, because we do vary it from time to time. So today we're going to be looking at the question, what does fully optimized really look like? And that's kind of where we started this conversation. And we were looking at sort of the marriage between AI and additive manufacturing, or artificial intelligence and additive manufacturing. And if you're anything like us, like artificial intelligence is this new amazing technology, and it's going to be a significant part of our future in a lot of different ways. I recently had some trips with my daughters. We're looking at colleges, and I wanted to challenge them. And I said, you know what, be ready for the question when you go to job interviews, what can you do that AI can't? And I think that's something to look at. It's changing all the time. It's not enough to answer that question once. You have to kind of keep answering that question every month. So if you're joining us today, you're going to get a great view of that, and you'll be able to answer that question when it comes around. So let's look at fully optimized for a second. You know, when designing for performance, you still have to consider things like material properties and manufacturing. Those are known things that you got to take into consideration. Additive manufacturing is changing both of those in a real-time basis. And conceptually, the better the materials and the less limitations you have in manufacturing, the better the part. But can you actually get there? And how do you get to a perfect, in terms of what we can do today, part? Today we have with us the founder and CEO of PhysicsX, and we're going to crack open this question. We're going to dive into a little bit. Let me bring on Robin. All right, there we go. Today joining us is Robin to Luis. I hope I got that one right. Founder and co-CEO of PhysicsX. And we're going to talk about looking at additive manufacturing and looking at artificial intelligence and see how the two go together. And we're going to dive into this a little bit. As a reminder, today's session is a live show. We're doing it a little bit earlier because we have our European colleagues here on. But we love to hear from you. We love to get questions, and we want to answer those questions real time. There can be a slight delay between when you ask the question and when we actually see it, so please account for that. But with no further ado, let's dive into this session. Robin, can you give us a little bit of your background?
Yeah, hi. Well, thank you for joining, and excited to be here. My background is I'm a physicist, a theoretical physicist. Ventured into numerical physics because all the pen and paper problems were solved, and so the hard problems remained, and for that you needed to solve them numerically. Spent some time in academia doing that in the U.S. And then left and went into Formula One. We are sure stopped somewhere else, but because in Formula One you can very, very quickly find out whether your theories are right. And that's just not true when you're trying to do numerical physics on gravitation. It takes a while to find out if that's true. And so speed of development was sort of the urge to go into Formula One. And I was chief scientist for Mercedes F1, head of research and development for Renault F1 before that. But speed of development is really important, theory versus experiment. What's the result? Is it true? And you get that in F1 because you find out on Sunday whether your theories that you've been working on in the weeks and months before are true. And what we'll talk about today also is that there's even a higher acceleration that we can get out of simulation, where we go with deep learning surrogates, and what that really means for optimization, as you said, Mike, in the very beginning, how we leverage that speed. That's my background. Founded PhysicsX 3.5 years ago. We're a team of scientists and engineers, about 35 people right now, growing quickly. And we deploy advanced simulation and machine learning and deep learning to solve hard problems in industry.
And so let's talk about the product a little bit. So how would you describe your offering to the market?
Well, we like to help our clients solve very hard problems and do that in repeatable ways by assetizing the solutions and essentially creating software around that, so that it's repeatable, the client can operate it, we maintain that, or help them on a support, or long-term support. But you should think of this the same way that people thought about, let's say, CFD 30 years ago, or finite element analysis that long ago. It took some time to really understand what that meant, but nowadays the packages are executable by students, right? You don't need to be an expert to run the package. Yeah, they're hard problems, and for that you absolutely need to be an expert. I'm not minimizing it here, but the basic operational thing of that has become very democratized. And this is the way we think about machine learning: is to democratize that and make it available, so easily consumable. Create workflows around that people can use, and really with the aim to optimize their products to across a number of advanced industries. So we're talking about renewables or additive here, or automotive or aerospace space, um, sustainability, medical devices. We'll have an example there.
Awesome. And you mentioned this idea of a surrogate. That was new language for me to understand. Could you talk a little bit about what you mean when you say deep learning surrogate, and then we'll kind of go into how that's applied later. But I think that's really interesting language. It's new to me. Is this something you hear in AI? Is it an AI term?
Yeah, I mean, surrogates actually have been around for a long time. What does that really mean? It means that rather than solving the numerical equations, let's say Navier-Stokes equations in CFD, I have some proxy. I have something that is much simpler to solve. It doesn't actually solve the numerical equations. It might just be some correlation that I have, between the size of an opening and the drag it creates, right? I mean, we have analytical solutions for things like spheres. So in a way, that becomes a proxy for doing a numerical estimation. But what we're really talking about here is far more complex surrogates. And these are not just the things where I go by, let's say, I change some geometric parameters and I get out a different pressure drop. If I really want to replace something like CFD, it has to look like CFD, right? So what does CFD look like? Yeah, CFD looks like this. I have a full geometry. That means really the mesh of the part, the whole geometry, everything, not just a set of numbers. And what do I get out after that? After I've meshed it and solved it and post-processed it, well, I get pressure fields and flow vectors, so vector fields, pressure fields. I get scalars, so like drag and lift and things like that out as well. If I do heat exchange on top of it, I get effectiveness of the heat exchanger or delta T, whatever else, temperature maps. So the surrogate has to look just like the CFD, right? So it has to predict all of that. And that's exactly what we do. We ingest the entire geometry and turn that into an output that looks exactly like, let's say, CFD, if that's what we're solving for.
And we
And,
kind of have this image here, sort of comparing the two. And I'm really drawn to the time in the bottom. Like you've got CFD taking hours, and then you have your surrogate model, which can be done in seconds. It's amazing.
Absolutely. This is the advantage. On the left, solving Navier-Stokes equations on a grid takes a lot of time. You got millions of mesh elements, so you got to solve it for each one, and then the solution has to iterate into a stable trajectory. And again, that takes hundreds, if not thousands, of iterations, depending on the solve hours. Some takes a long days in case of unsteady flows, and so the meshes too. Um, oh, it seems we've lost the image. Like,
Oh yeah, I was just going to listen to
oh,
you for a little bit here, and I wanted to bring this one up too because you mentioned kind of going through those multiple iterations. I thought this was amazing that you're able
okay,
to sort of create this new frontier of design.
yeah. So the speed, just in the previous slide, just very briefly on. So the speed is the surrogate. That's just a deep learning model. It's a much simpler calculation. It runs on GPUs. It goes very very quick, and so therefore the inference that is given a geometry and it gives you a CFD like result back happens in under a second. Yeah, sometimes a second, sometimes a tenth. It depends a little bit, but on the order of a second, which is much quicker. It's not any more accurate. Sometimes you can. There's some things you do, but the accuracy side to make it exactly the same, or in some cases even a bit better. But the thing is, it's just the speed. We're exploiting speed here, and when you have a deep optimization space, so a lot of geometrical variation, it's very hard to do that in CFD because it just takes a long time to optimize. Even with the best optimization techniques and the best machine learning optimizers wrapped around it, it just takes a long time. So here what you see is actually when you play this, it's a video, but we just got the static image up here. On the top, you can generate the geometry very quickly. It's another thing you've got to learn how to do is parametric geometry will take minutes to update, sometimes longer. So, well, we don't want to wait minutes if we've got something that solves in under a second. So we've learned to generate geometry very, very quickly, evaluate with the surrogate very quickly, and then on the right, you see a little flow field output for that modified geometry. Now in this case, you can see it's a brake duct on the corner of a car. And when you look at this plot there, what you see on the two axes are two performance parameters. In one case, on the bottom axis, it's like brake cooling, it's heat transfer to emission. On the vertical axis, you've got mass flow for the duct, so that's like car drag, right? And I want to be in the bottom left. That's where all the performance is. The best brake cooling and the lowest car drag. And the gray dots is sort of where I get to with CFD. You know, a reasonable amount of time over a few weeks, I can optimize to where that red line is. And then when I run the surrogate, well, that can run a lot faster. And so I can do 1 million runs in a week. And because I have more design space exploration, I can be intelligent about that with my optimizer. I can do intelligent search. I get to a new line, the blue line. And that blue line, actually, it wouldn't get, even if we run more optimizations, it doesn't go any further, and no matter what we do. And what we found there is the limits of the physics. That's the true Pareto front. So if you want to make a brake duct that starts here and ends there, no matter what you do with the geometry, can't do any better than that. You can trade cooling versus drag. So, and this is the thing, you know, it's actually very cool if you think about it. You get to the limits of the physically possible.
And so you've got kind of a learning model that's fed by CFD. That sort of seems to be the first stage. And then you've got a surrogate that's formed, and that's where the AI comes in, is to create the surrogate?
Yeah, the surrogate is, it's a deep learning model. And then, you know, it's not just about the surrogate, let's say, or the geometry that is generative. It's about also the entire workflow. That's the important bit, and how you control that. There's an optimization piece to that, and there's other pieces in this entire pipeline. So you put all of these together, it becomes an intelligent workflow that can operate by itself and automatically so.
And now you've got millions of iterations that creates a different boundary condition or a different frontier of what you're able to engineer. And then do you go back and like reconfirm that with CFD as well?
Absolutely. Yep. You can you know, and please do keep in mind that workflow, it doesn't have to work on CFD. That's an example. We can also ingest experimental data. We've done that. You can do both. So you reconfirm with your validation tool. So if that is a simulation tool, if you've got a highly well-validated already good simulation tool that you trust, validate against that. If it's experimental data set, a lab test, or some metadata, validate against that. The thing it saves you is all the time of development in between. You know, because you make that much shorter because it runs faster. At the end, you still need to do your validation to be sure. You know, you wouldn't release a part without.
And then in a reasonable time frame, now you've pushed the boundary of optimization. Like you've come up with that perfect design almost.
Yeah, it's just compresses that development time very quickly. Goes back to the beginning. Gravitational.
And we do have some examples here. I know this one I know a little bit more closely. This is what some of the work you've done for Velo 3D on our side. And maybe you could talk about this process here.
So what we've done, the challenge here for Velo was to keep the laser window clean for a long time, for weeks and weeks. And if the laser window is not clean, then when there's a soot that's deposited on the window, it heats up the window, creates a thermal distortion of the quartz window, and that of course misdirects the laser beam or affects the laser beam in unwanted ways, and you have to stop the build and clean it. And so we created a near perfect 3D air curtain here, and we did that by optimizing the geometry. So all these little turning vanes that you see there and the holes and whatnot, going from something that is very turbulent flow, so this unsteady flow, and turning that sharply, and then creating a very nice smooth air curtain. That was tricky, and you don't really get there by the typical design optimization that you do by hand and learning that would take you a long time to get there. Here you set this up and you use a machine learning algorithm around that to really drive this automatically, robustly to the targets that you define. And there's targets for consistency that we defined, that what we thought mean a strong or consistent air curtain would need to meet. So no
and I've
recirculation
seen
out to the window, for example.
well, and I've seen these on every Sapphire XC that we ship out there. Just for reference, kind of this is what the system looks like. This system has 8 lasers, and every single one of those lasers has that nozzle on it to keep that soot, that metal powder, from accumulating on the window. And it has definitely pushed how often we need to PM those windows. Like the example you're giving, you go from every build to now once a quarter. And the confidence you get because you don't get the lensing, the thermal lensing, and the distortion in the laser is amazing. There's a part quality impact there. So amazing work. We've absolutely enjoyed it.
Well,
I do
yeah,
want
just one point on that. Of course, it's also printed on a Velo 3D machine, so we work closely together
that's
to understand how we actually what geometries we could optimize around and what some of the other constraints and opportunities in the build are on a Velo machine. So it's the machine printing itself.
Yeah, which is has its own sci-fi elements to it too, but that's actually a good segue into kind of incorporating manufacturing. So you can simulate. Let's say we're just doing a CFD side thing, not using the real world data, but you use CFD, you simulate a part, you confirm it. Now you have this amazing design. How do you know that it's manufacturable?
Well, that's precisely because we work together to understand what manufacturable means. And of course, it means different things in additive than it means in other industries. And so we understand, and we have actually defined a process. We've trademarked it called SPAM, Simulation for Additive Manufacturing. And what you looked at for there, for example, is simulation for additive manufacturing. And the for additive manufacturing means that we understand what we can do possibly on the machine in terms of geometric parameters, in terms of surface finishes, build quality, material properties, and all of that. And we ingest that into our optimization.
But not everything you make is additively manufactured. There are designs that you're making that are conventionally manufactured as well.
Yes, yes.
Okay, so it is applicable for pretty much anything you want to fully optimize.
It is, but there are some hard problems for when we talk about castings and things like that. That can be quite tricky to understand that because then you also have to talk about the casting process and the different casting processes and the vendors and whatnot. So there's a limit, and let's be clear here. This is not a fully matured technology yet. There's also a limit of what you can do right now in terms of manufacturability assessments. But in the first instance, certainly on the design cycle side, you can get to the best design.
And so, we've kind of talked about this. We sort of baited the hook. We've dangled the hook in front. I think it'd be interesting to talk about how people can access this service. Like, what's the process look like for them to reach out to you, to have that conversation?
We have a website. You can reach out through us through the website. You can reach out through us through Velo 3D. We're very much a business to business operation, of course, and then we want to understand what your pain points are. What's bottlenecking your development process now. We're deeply experienced engineers, and we can help you find a solution to that. And let's be clear, not every solution is a machine learning solution. Not every solution is a deep learning solution. You need to solve the problem for the client and create the right tech stack for them to do that. And sometimes they're just simulation solutions, well arranged and made into robust workflows.
Just taking a quick check here for any questions. Looks like we have a lot of people saying hello. So you have a lot of fans out there, Robin. And just a reminder, if anyone has any questions, we're at the 20-minute mark. We're going to have about 10 minutes left. I'm kind of saving a big story that Robin's been working on, a heartwarming story. And we're going to have that at the end. But I would love to hear if anyone has any questions around how AI is working, the functionality of it, or how it's interfacing with additive manufacturing. Please let us know. We'd like to hear from you. But I do want to step in and kind of what, so you mentioned that they've got to come to you as an engineering firm and bring in their problem statements. Do they need to decide on a manufacturing process, or is that something that you find your clients are open to changing their manufacturing process on?
I mean, this is a really good question, and of course, the migration of manufacturing processes from legacy process to additive, and that's what we really want to empower and encourage here. And coming back to additive, DFAM, design for additive manufacturing, essentially takes an existing design and modifies it so that it is printable, but it doesn't really exploit the performance that we can get. So, and that's what we're about. So, when you come to us with an existing design, and particularly if you have an inclination about maybe wanting to do this in additive, then we can help. And we have done that in aerospace, for example, quite a number of projects like that.
And are you able to say, here's your design, if you need to conventionally manufacture it, this is what you could get? If you move to additive manufacturing, there might be a case B where there's better optimization. Do you see that?
Yeah, absolutely. Absolutely. This is, I mean, the move to additive manufacturing has to be motivated by something, doesn't it? And the design freedom, and the better the machine, the more the design freedom, in our opinion. Of course, that unlocks performance. And is that performance worth, let's say, whatever the business impact is on going to additive? And we see cases where it absolutely is. I mean, you do. This is Velo's business, isn't it? The performance gain is worth the additive cost. And we see the same thing because of the performance unlock.
Well, we've definitely gotten some questions in. I think people are excited. They just wanted to hold their questions until we went through some of the other material. But there's some really good ones, and I want to dive into this for a second here. Does AI design able to take into the factor of safety? I think this is an interesting one.
Yeah, fantastic. Well, look, let's say we're predicting stresses, right? Let's say we have a highly loaded part and you want to do some weight optimization, and in your FE, you would predict stresses on that part under a given load condition. We predict exactly the same stresses, only quicker. And then you have a factor of safety that is a constraint. So if you optimize against that constraint, exactly the same thing. The answer is yes, clear. Same process as in the FE. So your maximum stress would just be multiplied by the factor of safety, and that has to be below, let's say, the yield stress or the fatigue stress, whatever loading condition you're considering, whether it's cyclic or ultimate load.
Okay.
This is field. Yeah. Sorry.
Well, one of the questions here is for metal additive manufacturing, and it looks at, is AI being applied to post-processing in metal additive manufacturing, predicting warp, dimensional change? Have you had any experience with that?
It's a fantastic question, and no, we haven't done that, but it's a very important thing because, I mean, I don't see in principle we couldn't. But if there's some CFD, I'm sorry, if there's some FEA ground truth where we predict the warping, and there are packages that can do that, we can train on that and just do that more quickly.
Okay.
But the problem sounds simple on the surface, and you have to dive into it and see really what the complexity is. So I would say in principle yes, and practice, let's see.
Yeah, it's sort of an interest. I'm trying to wonder how. I think with what we're working on, because it's fairly dense material, this user does ask about centering, which you do get a lot more of a change in the dimensional characteristics. So that would probably be something. And Mark actually asked the question. I think I'm interpreting this right. Is who sought out who? And I know you have a relationship with Benny, but I'm curious. Did Benny reach out to you first, or did you reach out to Benny? Where did this relationship start?
I knew somebody that had joined Velo, and I've been working with Additive for over 20 years. And when this person joined Velo, of course, we started talking together and ideating together, and that's how the relationship formed. And Benny was interested in what we are doing, and we recognize Velo as a phenomenally capable company in additive that can do things nobody else. So it's kind of a good mix, a good partnership.
Nice. And I do want to go through kind of this last story. I think this last story is pretty powerful. It's another use case that you've talked about. And I'll let you sort of set the stage here. So let me get that image up there. Okay, so this is one, and we got like a picture of a heart on this.
Yeah, that's right. So what we've got here is we've got an artificial heart on the left side, and you've seen early prototype sitting there in your left ventricle, right? And that thing is just a mini turbine. It's a mini pump, sorry, mini Francis pump. It's got a wheel, spins around, electric motor, contactless, all of that, and it pumps your blood when your heart has failed. So it's great, you know. People have a heart attack or heart disease, degenerative condition. It's a lifesaver. The only problem is there's lots of complications. You know, this technology exists. You know, things are a bit clunky and big right now, but they also cause damage to the body, and the damage is that it damages the blood. And the way it damages the blood is that the blood stays too long in the heart pump, and then it coagulates. You know, forms a blood clot, or it shears the blood. So in this case, let's say we look at the shear damage that's created by the blood. We can calculate that. It's hard because blood's a very complicated substance, much more complicated than water. And so understanding the damage mechanisms of blood is important. Of course, the flow performance of the pump is as well. And, you know, the CFD simulation used to take several days. And then we have been able to accelerate the CFD itself to 1.4 hours, but that was about it. So just by being good at CFD, we were able to do that. And then we accelerate that further with a deep learning surrogate. And we can predict, you can see on the left is the CFD result, on the right is the surrogate result. For geometries that the surrogate has never seen, it predicts at well over 90% accuracy, and it does so in under a second. And then by optimizing that geometry, which are the blades, we've also done work for this client on the inlet, on a few other things of the heart pump. But in this particular case, we generate about 40% more flow performance just by the blade optimization. And what that does is that when you do that and you reduce the blood damage, it takes less power. And then if you use less power, you don't need a cable coming out of you. You can have a transcutaneous, which is a wireless energy transfer. People don't have to go to the hospital for infections with cables anymore, and they don't have to go to the hospital with internal bleeding issues because their blood's been sheared. And you reduce all those post-op care costs, which are the large costs of this. It's not the pump or the first surgeries, all those complications later. And that makes it affordable. And it makes it affordable in the UK from the National Health Service and also around the world. And that's the impact you can create with optimization, which is pretty cool, I think.
Yeah, it's amazing. So everything from aerospace and rockets, healthcare, Formula One, obviously, and I understand I don't know how much you're able to talk about this, but you've had some success in some racing industry recently.
Yeah, I think we're
with some of yours.
You know, the examples we showed you, we have permission to show. I mean, we've done lots and lots of these, 50 some of these sort of cases, and so we don't talk about that. I'm afraid I can't say we did well, very well. So, but it's the stuff that gets you out of bed in the morning, working on these really exciting problems across industry. I think the whole team behind me here is really excited because we touch lots of cool hard.
Yeah, absolutely.
Help people really make a difference. Yeah.
Well, I am curious. So there was a question that somebody asked, and kind of looking at these designs up at the top. So you have this learning data that's fed in to the model. Sorry if I'm getting some of the language wrong. How free is this model to come up with something maybe radically different, or does it tend to pretty much stay, like, what are the boundary conditions?
Well, radically different geometry depends what you do on the front end in terms of the geometries that you want to optimize over. The question is, how accurate is the model in predicting the real performance of those radically different geometries? And that is quite dependent on the type of model that you use. If you use a purely data-driven model, it tends to be okay, close to the edge of what we call extrapolation. For interpolation, absolutely fine. Within the parameter space of geometries that you've traded on, it tends to be quite okay within that, and we understand the uncertainties within that. But when you start extrapolating with just a data-driven model, there are definitely limitations. But you can integrate different features into model that allow you extrapolation. Well-known models, for example, pins, physically informed neural networks, are able to extrapolate a far away because they learn understanding of the physics equations as you go away from the trained data, which is what extrapolation allows you to do that.
This is pretty amazing.
To answer the question precisely, for data-driven models, you can't extrapolate far.
No, it's pretty amazing. The idea of anything pushing the boundary of optimization, pushing the boundary of performance, finding any sort of edge on the competition or edge on the physics. I mean, I think more people are competing with the physics at this point than they are with other companies in a lot of these industries. But being able to have that edge it's just key in all these industries. Amazing job. I do want to ask, do you have any parting thoughts, or where do you see this going? Let's say 5 years from now, we have another 3D and 30. What are we talking about in 5 years that you think
God, it will have. The thing is, I mean, the landscape of the methodologies and the applications is changing exceptionally quickly. I think this is here to stay. I think this is going to be increasingly important in businesses and in the competitive world, and your time to market, bringing your product to market quicker, and also extracting performance and creating differentiators between your own products and by that I mean our clients' products and the competition that they see out there. It's the same journey as CAE has taken. You're not going to be on the map anymore if you don't use CAE in your development process, right? CFD, FEA, multi-body simulation, all of that, relic mechanics simulation. You need to do that. And similarly, in 5 years from now, I think it will be a key performance differentiators for companies who can deploy AI effectively in their product development process.
Yeah, awesome. Well, thank you, Robin. Thank you, audience. Thank you for the questions. I know there's some very technical questions. A lot of times we like to go back and invite our speakers to answer those directly on LinkedIn. So stay tuned to that channel and look for the conversation, and maybe some of these become really good dialogues that carry forward commercially too. So
yeah, I see some great questions there. There's some people that are actually that seem to be quite interested in the field or working in the field. So thank you for
I think so. All right. Well, and that's a wrap. That'll be our 30 minutes for today, or 33 minutes rather. But thank you, Robin, again, and thank your audience for joining us. Awesome session.
Great. Thank you very much.